Okay. So, okay. So yeah, I haven't really. Well, I looked at it once and then I got very scared, so I left. Yes. Did you want to work on the specific one that you were having trouble with, Lupita?
Oh God, which one? All of them?
Oh, okay. Is it? Oh, okay. Then we could just go through it also.
Um, it's up to you. There's like a few that I don't understand, but I don't know if you want the specific numbers or you just want to go through them all or some of them.
Yeah, I'll just go ahead and go through them all then. But also, yes, I don't know for sure if I'm doing things correctly, and Chelsea isn't even here to correct me, which she always does. So yeah, we're all just gonna kind of do it together. So this first one is IUPAC naming. So you'd start off by numbering it. So, I mean, I'll just kind of ask you guys, would you want to number this one or this one? Or well, I'm sorry, this is the carbon for this carbon.
Well, that's what I was having a hard time. Does it matter which one, or does a bromine come first because of alphabetical order?
I don't think for this one, yeah, you know what? I honestly don't even know like for sure if there's a rule about it, but I mean, I don't think it's alphabetical order, but I do think that just because this has a methyl and a bromine on it, I would label it one.
Okay.
Yeah, but honestly, well, I'll ask her about it tomorrow in her Zoom meeting because yeah, I don't even know the actual rule for like a lot of cycloalkenes. I feel like those give me a hard time a lot, but yeah, this I definitely want to say that this one would be one because it has two things attached, so it would be higher priority anyway.
I have a quick question. Like, what if we get most of this done today? If we go to her Zoom tomorrow and ask her to clarify if our answers are correct, will she tell us if they are? Or will she like beat around the bush?
I honestly don't go very often. I feel like I've only heard that she beats around the bush. But yeah, if you have like a general question that you could ask about it, then I mean, you'll be able to get a straight answer.
Yeah, if you're asking for the answer, she doesn't really give it to you.
Mm.
So yeah.
But then for this one, you could definitely, I mean, this is a good example problem, and then she'll go off on a tangent of however you're supposed to actually do it. So yeah. Yes, but for this one, so yeah, I'll just label this one number 1 for now. I'm pretty sure that'll be right, but we'll clarify tomorrow. Here, wait, I'm gonna write it. I'm gonna have a sticky note right here with questions to ask her. So yeah. Anyway, so yeah, so this is one. So I'm gonna go around, pretty sure, because it's dye substitute. That's what I was saying. Like I'm pretty sure, but I don't know the actual rule for it. But yeah, so we'll just go with that for one.
Yeah. So then, okay, I think I got the name, which is going to be 1 bromo, 3 chloro, 3 methyl cyclohexane, right? At least somewhat like that.
Probably. Yeah, I'll just go ahead and do it and then we'll go ahead and see. So I always start with the end of the name. So yeah, so it's cyclohexane. Oh, right. Okay, and then just go off on these ones. So this is a 1 methyl, and then this one is 1 bromo.
Oh, yeah.
And then this one is 3 chloro. And then from there, I believe you could put it in alphabetical order. Mm-hmm. So 1 bromo, 3 chloro, and then 1 methyl cyclohexane. Is that what you said earlier?
Yeah, I said 3 methyl, but I got it wrong. It was 1 methyl.
Oh yeah. Yeah. No. Cool. T's. Yeah, alphabetical order is basically just like once you're putting each of these, like this is a methyl. It's actually I think it's just for the substituents or whatever they're called. There's something like that. Yeah, and then chloro. And then from here you put it in alphabetical order. Yeah. Okay. Is that cool for everyone?
So the part that I got confused was, do you use R and S? Because I believe EZ is alkenes.
Yeah, that's true. So definitely not that one, or well, I guess for this one, whatever. Yeah, not that one. Not RS for this one because she said there's a note in the
Yeah,
in the
I
last
think
one.
I think I know what you're talking about. It's like
Yes.
only when wedges and dashes are drawn can R and S be determined.
Yeah. So at the next one we could definitely do RNS. Cis and trans. I don't think that applies.
I don't, okay, yeah, I don't
here.
think so either. So
I'll
that's
go
just
ahead.
what I got.
Yeah.
Okay.
Is cis and trans also for alkenes only?
I think if
Yeah.
other group
Yes, I think so.
four,
Okay.
it could be cis trans. Or like if
It's-
it's the you know the ring structures we did for like the glucose or whatever, and then like if it's both up or down.
Wait, what was that?
Like remember when we were doing like the axial, equatorial, and like the chair?
Oh,
ring? I think that can also be cis trans if it's like on.
Oh, that's true. Yeah.
Like the
that is
dye
true.
substituted rings.
Yeah. But I guess,
Yeah.
oh my God, that might also be kind of different because in that one you can tell which way they're facing and stuff. I don't know. Okay. But yeah, yes, I guess everyone's saying that cis trans is for alkenes anyway. So
There's an example in the homework if you want to see it. It's on homework 7, number 10B. You don't have to look at it now, but that one is the chair one for that.
okay. Cool. Yeah, I still need to do the homework. I was just reviewing too.
Oh, it's almost like the same thing. Almost.
Oh, really?
Yeah, it's 1-bromo 4-methyl cyclohexane.
Oh, okay. Oh, and then is it also coming out kind of like that with 2 on one of them?
No, they have it in the
Oh,
chair
okay.
model. That's why.
Oh, okay. Does that one say cis and trans though?
No, I didn't put any of that.
Oh, okay.
So I don't
know
know.
what it
For
says
me,
the
I'm gonna
actual
say
answer.
no.
Okay. Yeah, and then we also have tomorrow, and then I can double check with her about that. Yeah, so that'll be my next note. Okay, so yeah, I'll just go ahead and clarify that because also I can guess myself. Okay, cool. So then, yeah, otherwise we could just go ahead and go to the next one. So this one, I mean, so first you would number it starting from here because this is the first
It gets priority.
thing. Yes. 2, 3, 4, 5, 6, 7. Okay. So then you start with the end of the name, or well, I do so. And then it's
heptane.
pentene. Or oh shoot. Whoa, heptane, yeah. Heptene, yeah.
Mm-hmm.
I almost called it pentene. Okay, cool. Oh, and then you also need to clarify where the double bond is. So 1 heptene. Cool. And then so this one is gonna be 3 iota.
Mm-hmm.
And then these ones will be 4 difluoro. Yes.
Wait, since it's at UPAC, she'll probably correct you on like the naming. So it's FLUO. Fluoro.
Oh, really?
Yeah.
Wait, so how is it? FLU?
UO. Fluoro.
RO or
Fluo. Or
really?
fluoro, sorry, yeah, RO.
Oh, okay. Yeah.
But it's FLU though. That's what I mean though. Yeah.
Okay.
There you go.
Okay, cool. Did not know that. Okay, cool. So yes. So then from here I would do alphabetical, and then I'm quite sure I don't have the rules in front of me, but the die does not count. It's just the F, right?
What was that?
When you're putting it in alphabetical order, like the die, like saying that there's two of them, that does not count. You go by the floral.
No.
Yeah.
Yeah.
Cool. Okay. Okay.
Don't forget to
There's-
add a 4. Another 4.
Oh, 2 4s. Yeah.
4 dash
Okay,
4.
cool.
Or 4, 4. Sorry, 4, 4.
Yeah. Okay. Cool. Do those go in parentheses? I feel like sometimes they do. Meh.
No,
Probably
I
doesn't
haven't.
matter. Not that much. Okay, cool. Yes. 2 4s. Yeah, okay. I just write it out there. Okay, yeah. So then otherwise, we'd do R and S. So we could do R and S for both of these, I'm pretty sure. Yeah. So I'll erase these. Oh, wait. This one is the same thing. So this one does not get R and S.
Because you have to have 4 different groups, right? It's not 3,
Yeah.
it's 4. Okay,
Yes.
so that one doesn't count in the I.
It's for chiral.
Yeah.
Or chiral ones. So not this one, but this one, yes. So this one also has a hydrogen back here. So, well, that's interesting. Well, I'm pretty sure that, well, so yeah, so this is 1, and then I'm pretty sure this one would be 2 because it has 2 fluorines, but this one has 1 alkene, but oh
But
no,
isn't the
it's
double
F.
bond
That just means
CC?
it's, yeah, exactly. Okay, yeah, cool.
Yeah.
Exactly. Okay, cool. Yeah, so that one's attached to fluorines, so it's different. So yeah, so let me just take a picture. Okay, so yeah, that one's 1, this one's 2, this one's 3, and then I mean this will be 4. So when it's when it's wedged, that means that it's gonna go in this direction, or like just the direction it's already going.
Clockwise?
Yes. So clockwise is
For the hydrogen,
R.
right? Yeah.
Yeah.
Okay.
And then you also need to wait. 2, 3. This is our third one. So 3 are in the beginning.
You had to put the 3?
Yeah, you do have to show where it is on the thing, the
Okay.
chain or whatever. Yeah.
And then I
Oh.
wanted to ask, can it be cis and trans, or is it a no because the end, because of the double bond?
oh.
Would that be geminal?
That's a good question. I think, yeah, no, this one is not going to be cis and trans, but I didn't even notice that, but yeah. So it's not because, I don't even know. Yeah, I think
Ew.
it is considered geminal actually.
Because of
yeah,
the H,
these
right?
are the same, so it wouldn't be.
Yeah.
I think it would technically be geminal, yes. But yeah, so not cis and trans because it's all the way at the end.
Okay. Okay.
Cool. So yes, that's that one. And then yes, we did that one because it has wedges and dashes, because otherwise we wouldn't be able to tell what direction it's going or anything. Yes. Cool. So that one cool for everyone.
Mhm.
Okay. Cool. Okay. So then number 2, predict the products. Okay. So at this point, I would definitely have my notes out just so that I remember all of them. So for Lindler's catalyst, where is that one?
That's on page 512. Page 12.
Okay. So yeah, so Lindler's, it turns a
It produces a
Oh.
cis alkene, yeah.
yes. Yeah. Okay, so then I feel like I'm bad at these, so I'm scared. So I think the first step is gonna be right. So, oh, you know what? I'm scared. Wait, hold on. Let me see. I don't think I have any examples either.
Well, my concern is the HBr because so far the examples that she gives are just H2 and Lindler's catalyst. And then
Mhm.
the HBr is a different one. So
Yeah. So you do one after the other. I know. It'll work out because it'll have a double bond at the end. Let me go ahead and see. I think I'll go to the notes for that one actually, just so that we can all see. Is that chapter 5?
yeah, chapter 5,
chapter
page 12 for Lindler's.
Cool. Okay. So can it show me? Nope, this is it. Okay. Let me see. So yeah, I guess you literally just yeah. Oh, okay. So yeah, so you're literally just like taking off one of these double bonds and then you're taking those hydrogens out. So yeah, that's what happened over there. Okay, cool. So but that one's a terminal one. So let me see. This one. Take this one out, and then you have oh my god, I hate this. I actually don't know.
So the way I did it, and I'm probably really, really wrong, is I did a cis alkene and I had the methyl and the bromine together on the same side. But I'm not
what did you
confident
do for
about it.
just the first step?
I
Do you
just
know?
drew the cis alkene because that's what the Lindler's catalyst produces. But the
Okay, yeah,
HBr
so you
is
just kind of went for
confusing.
it. I'm just
Yeah.
yeah, I guess I'm trying to make it make sense, but I don't know. Because I guess I am not sure what to do with that part or where it goes. So yeah, definitely this. And I mean, yeah, it has to be like that at least, but I don't know if that one is gonna
So what do you mean that the one you circled? Like that methyl
I don't
group?
know if that one is like yet another one that's gonna be like over here. Yeah.
No, because isn't that 3 carbons though?
Let me try to see that. Yeah.
That's
Whoa. Is this a carbon? Yes. Yes. Yeah, I guess we should just have what? I was
So,
gonna say
yeah.
we should have the same amount, but here we have 4 now, right?
Yeah, but the way I did it was with one of the C's up top, I put it as the BR, but that's where I'm confused.
Yeah, because I know, well, I guess I don't know how they work separately because this terminal one. We could maybe come back to this one in a second because
Yeah.
So for this one, I mean that's just someone said earlier hydrohalogenation.
Yeah.
So if you did that to like, I guess one of these, what would it do? Oh my god, add a hydrogen and then the BR in it and Markov-Nikov issue. So the hydrogen goes to this one, and then you'd have a BR right here, I guess, or like I don't know. It's too many, isn't it? Is it? Wait, 1, 2, 3, 4. No, I guess not.
Hydrohalogenation, the H and the X, which will be the bromine, will be on the same side, right?
They go to opposite sides of the double bond is why. So this is my example for it. Or like
hydrohalogenation?
Yeah, so I have it like on a little piece of paper. So this would be okay. So just an example of hydrohalogenation. It's like this. Yeah. So so this would attach to the hydrogen, and then this goes off by itself first. For the intermediate stuff, I guess. And this one. So then it lost the double bond, so it's a carbocation. Oh, I gave myself a hard example because then you do a hydride shift, so it'd be like this. So then now you would add your hydrogen. No, wait. Well, the Cl is just going to go right here because it's negatively charged. So there. And then this is a hydrogen, but whatever.
No, that's halogenation. So
Well,
you
yeah.
have hydrohalogenation and then you'll have halogenation. If you're talking about they're
Wait.
both on opposite sides, that would be the halogenation, wouldn't it be?
No. Okay, yeah, no. So hydrohalogenation is when it has a hydrogen in it, and then halogenation would just be like Br2. Just because I'm like looking at it right in front of me. So those ones are like exactly the same. That one would add like Br. So that one's halogenation, but hydrohalogenation, one of them is a hydrogen, and the hydrogen goes to the carbon with more hydrogens. Yeah. So you get a hydrogen here and then a Br or whatever here. Hypothetically. But I can even get past the first step for this one. So we could come back to this one in a second. I think I would probably have to watch like a little video on it or something. Definitely need to refresh that one. So yeah, so we could come back to it. Maybe, does this one make any sense? NaNH2.
Yeah, that one's also on page 515. That one's a two-step process that you can do either all in one step or all in two steps. Oh, sorry, all in two steps. But she had it two ways to do it, if that makes sense.
Okay, let me see.
So it's just page 515. And the way I did it was the H is gonna go away.
Let's see.
On
well,
the alkene. Or the
yeah.
alkyne, sorry.
Okay. Let me see. So the NaNH2 is deprotonation, I'm pretty sure. Yes. Okay. So this one isn't deprotonated. Oh, but it'll make it deprotonated, I guess. Yeah, okay. Yes, this one goes in combination with yeah, these ones. Okay, so yes. So this one deprotonates. Basically so that this can happen. Yeah, and then it basically just touches, right? So it's just like, I think it would just be like that, but I might be oversimplifying it. Is that what you got?
Yeah.
Okay. Yeah, because yeah, basically just add this whole.
Like, does the BR get added to it or doesn't it get kicked off?
No, the BR gets added. I don't know about the whole. Let me see if I could figure out the whole process, because I definitely like oversimplify it because the BR part's then. Oh, okay, wait. So realizing.
Because you create a new CC bond, and in the example that she gives, yeah, the BR gets kicked off in the example that she gives because it's a two synthesis.
Oh, it gets kicked off at the end.
So the way I did it was the CH, the methyl group on the BR just gets attached to the alkyne.
Oh, okay. I don't even know the process then, but okay. So you just keep the carbon.
Yeah, I'm just basing it off her example.
Okay, I trust. Yeah, so definitely we'll have to review this one. And then we could also, whoever's coming back tomorrow, we'll just go over the ones, whatever you need. So definitely those ones for me. And this one is literally the same kind of shit. So let's see. Yeah, we can, come back for these ones at some point. Let's see. So this one.
Excuse me, I have a question about the number 2, the last part. It should add a CH to the previous structure, right?
Yeah,
the
I
last-
added it right there.
Yeah, the CH3.
But I'm not sure it should add in trans or I believe
Oh, I didn't even do
this
that.
one, it should be add in trans instruction.
I don't. Well, I don't know about these ones. Oh, like actually, like being bent.
Yeah,
I
yeah,
don't even know if that-
and the other one is the
Um,
opposite
and
side. Yeah.
I don't know anything about that.
At page 15 in the notes,
Okay.
we have an example. She explained.
Okay, what was it? Page 15.
I'm not sure I'm correct, but I
Mhm.
remember she explained, and I watched the video
Mhm.
again.
She said it gets
The
added as
the
trans.
last, yeah, the end of the page. Go down, down. Yeah, here.
Okay.
Number
This one?
1 and 2. It's related to this question. It's very
Yeah. Oh,
similar. This question, I believe.
yeah, it is. Let's see. Mhm. Oh,
it is trans and key.
oh, okay. So I think is that this part it starts changing it to a trans alkene because yeah, I'm not even sure if it's considered cis or trans when it's an alkyne.
When it says NaNH3, that's when it gets transformed into a trans alkene.
Yeah. I think.
But we have NaNH2. That's different.
Yeah,
Oh,
that was
okay, I
the
got it.
first step. Yeah. Yeah. Okay.
Thank you.
Okay. So yeah, that was an attempt on that one. This one should be easier. So this one is gonna be one of the ones. Let me see. That adds the OH.
The only thing I could have thought of was hydration, but I'm not confident at all on this one.
Yeah, let me go ahead and double check. So those are all the hydrogens. So for this one, the OH was added to the carbon with more hydrogens, which is anti-Markovnikov, right?
Mhm.
Okay. So then the one that is anti-Markovnikov with this is hydroboration. And I'm literally just looking at like all of the notes I have. So so that one is I hate these.
Hydroboration.
Yeah, so that one is the one. Well, this is just like what it looks like. I guess normally. So
Well, wouldn't it be Mark's rule?
what was that?
Wouldn't it be Markovnikov's rule? Because isn't it the carbon with the most hydrogen will get the hydrogen, or carbon with the alkyl substitute will
Yes,
get the
but-
halide? Yeah.
Yeah, but the opposite happened. So it's anti-Markovnikov, right? Unless I'm giving myself a stroke. Let me double check. Where do I have that? Markovnikov, the carbon with more hydrogens gets the hydrogen. So yeah, so if it was added in Markovnikov fashion, then this one would have gotten another hydrogen, and then the OH would be on this side, right?
Okay, so anti-Markovnikov rules is H added to the carbon with fewer hydrogens.
Yes.
Okay.
Yes, and then just like I just have the reactants written out. So this one's BH3 and like THF. I don't even know what that is. But yeah. We can, let's see. Yeah. So yeah, that's that side. And then we could like look at it because that one's kind of like confusing. Let's see.
Hydroboration.
Okay, yeah, so it's this one, hydroboration. Hmm. Yeah, I don't even know all the steps for that one. Yes.
So the
But
first step would be the
antimicrobial.
hydroboration, the second step would be oxidation. And then it would be synaddition, which is the same side. And then if possible, then you need to draw two structures. But yeah.
Yeah.
Okay.
Mm.
But that's all she's asking for, right? It's just what's on top of the
Yeah.
arrow and so forth.
Yeah, actually, I didn't even read the directions, so let's see. I'm pretty sure it was asking for reactants. Yeah, reagents. Or, yeah. Oh, and more than one step may be required, but that should be good. Yeah. So yeah, so that's that side, and then this one. Let's see. For this one, we end up doing like a. These are the same thing, but I think they're supposed to be opposite things.
Yeah, that's what she had the announcement on the front.
Oh, okay, cool. So yeah, so for this one, I guess it's saying that this would be a carbocation, I guess, once you take this off. And then they just switched it over to this one. So then a hydrogen is added right here. I'm not too sure about this one. Let's see. So I guess I would just like weed out the ones that are not with OH. So I guess it would only be hydration. Let's see if I can make it make sense. So H2O and then H2SO4. So this is hydration. And then it would add in Markov-Makov fashion. So yeah, so let's start from the beginning then. The hydrogen, wait, no, the carbon with more hydrogens is gonna get the hydrogen, so that's what it is initially. And then when we take this off, then we have this carbocation, right? 1, 2, 3, yeah.
Mhm.
So this one's gonna move over basically. And then it'll be there. And the hydrogen is still added to the one with more hydrogen. Let's see. I don't know if that's gonna make sense to me. Because I'm thinking that these ones are basically gonna have the same amounts of carbon if we're basically deciding between just like these two. They both only have one. Oh shoot. Sorry. Okay, wait, let me draw out the whole thing. Okay. So we take this off, or I'll just do it in white. So it's fine. So we take it off, and then we have just 2 hydrogens here. And then we have 1 here. And then this one's gonna have this charge. We also have a hydrogen here. And then when we do the hydride shift is what we're actually doing. We change that one over here, and then it basically just like switches. Oops. So then we have this over here and another hydrogen over here. So it adds in the Markov-Makov fashion. So we're gonna get another hydrogen here, and then this one's gonna add an OH over here. Yes, that makes more sense. I honestly kind of don't get the wedges and dashes as I'm looking at them. Wouldn't it be adding PT or PD? Let me figure out which one that one is. That's hydrogenation.
Yeah.
In hydrogenation, you add hydrogens to both sides. So no, because we have an OH. So I'm basically like, when I look at it, I'm just like looking at whatever's added, and then I'm going through like my little notes, and then I have that hydration and hydroboration both have H and OH added to it in some way. So yeah, it would be.
Yeah.
Yeah. Yes, but then this one is Markovnikov. So yeah, so I just leave it like that. It says more than one step may be required, and I'm not understanding why these are wedges and dashes right now.
So the bottom one, it's supposed to be
Yes.
switched,
fix it.
and the way I see it is, aren't they trans?
I mean, yeah, they would be, but I guess I don't know. It's probably, I'm guessing it's another kind of step that was added to make it like that, right?
That's what I'm thinking. So would it be the NaH3, because that's what makes it trans?
Oh, good idea. Okay, wait, let's see. Hold on. So, oh, I just drew it the same way. Shit. Okay. I'll just go into the notes to try and find. So what did you think it was? Let's see.
Oh, I said that to make it a trans alkene, they used NaNH3, but I'm not too sure if
Oh,
that's what
okay,
they
yeah.
use for this one.
Mm-hmm.
That's 512.
Yeah, NaNH3 would be. Is it? But is it technically even trans since it's a
I don't even know.
alkane?
No, I don't think it would be then, because it's an alkane, it doesn't have the double bond, and that one needs a triple bond to get to the double bond.
Okay. Yeah, I'm also not too sure about that one. So
Mhm.
it's another kind of question. I'll just add that unless anyone kind of no. Yeah. Oh, very over a year. Okay. Okay. Well, yeah. Yellow. We could go to the next one then. So determine the relationship between the following pairs. So well, just each of them. So 1 and 2. That's ugly. So first, I guess we can name them, or well, number 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. I'm gonna move those now. For this one, which one of these is rotated?
So isn't it for diastereomers, one of the bond has to be changed at least?
Yes, but this one looks like it's rotated down.
Yeah,
Is what happened. I have, let me see.
number
'Cause-
2 looks like it's rotated, so yeah.
Yeah, so I think that they might be the same. I'll go ahead and get here just to double check. I have a molecular model set, so I'll just try it in front of everyone who wants it. But otherwise we could look at the next one. Okay. This one, so these are different. These are different.
Mhm.
They are, well, okay. Well, I guess we could just already tell that these are the same. Or well, I guess, yeah, or you could say those are frick. I have a stroke. Okay. Those are all different except these ones are the same. So that just automatically means they're diastereomers. Because they would be enantiomers if they were all different. So diastereomers. Oh, but let me double check because it does look a little bit weird, just to make sure they aren't like totally different compounds. 1, 2, 4, 5, 6. 1, 2, 3, 4, 5. Yeah, no. Yeah. Cool. Okay, yeah. So those ones are diastereomers because these are the same.
What about number 1 and 2?
So yeah, right now we're kind of trying to just like double check on that one because it looks to me like this bond is just rotated like this. And they're just like the same molecule to me. So yeah, so I was just gonna check with a what's it called? A molecular model.
Thank you.
Yeah, so I'll go ahead and let everyone know right now. Does the one on carbon 5 count? Because there's not carbon 5 for this one. Yeah, I don't. It's not a chiral center, but it's just that for enantiomers, it happens when they're all different. So this one and this one are different, and then the OH ones are different, and the BR ones are different, but these ones are the same. So that just means they're diastereomers. So I don't think it has to do with chirality yet. This one, it's, I'm kind of, okay, wait, let me,
Like for that one, it's either gonna be B or they're gonna be D.
see this B or D enantiomers or,
I
yeah.
honestly think it's either,
Oh.
but I think they're the same compound.
Yeah, I think so too. I know, I'm like trying to get my shit together right now. Let me see. But yeah, how many carbons is that? 1, 2, 3, 4, 5, 3. Okay. Yeah, and then I guess when I'm reading this, constitutional isomers, can someone remind me of what that is?
They're the same functional groups, but are on different points of the carbon chain.
Oh, okay.
Yeah, so I think we can rule that one out.
Yeah. Yeah. Okay, cool. So this.
So here's my question. Can you have a structure that can be a diastereomer and an enantiomers, or is it either or?
It's either or.
Either
Yeah.
or? Okay.
Yeah, if you're looking at two of them, yeah, they can't be both because yeah. Okay, I'm about to share what I have. Give me 1 second. Oh. Okay. Okay. So I started sharing my face and stuff. So this would be what we have basically with the OHs on this one. So they're both going forward, or they're both coming towards me basically. And then the other group, it's basically turned this way and then just rotated this way. So this one's going backwards and then this one's still coming forward. So yeah, so they are what? The same compound, because yeah, it's just rotated like that. Yep.
Okay.
Yeah. Cool. Okay. So yeah. All right. And then yeah, does anyone want to check anything on 4? It's pretty cool.
Wait, so I just want to make sure I have diastereomers correct. It's when you have, it's almost like a similar compound, but one of the bonds is switched, it's either dash or wedged on the other
Yeah.
compound.
So basically, I think one of the definitions, like she has a list of stuff this one, diastereomers is basically anything that doesn't fit like enantiomers or like the same compound. So it's like mostly like what I go based off of is when all of because enantiomer would be if this compound, or well, let's just do it with this one. If this one were exactly the opposite and it were dashed instead, that would be an enantiomer. But a diastereomer is basically like when only one of those things happens. So just like if one of them changes and the other one doesn't,
Okay.
then it's like a weird intermediate thing.
And then enantiomers are twins, right?
Yes. Yeah, I think that's kind of what they
Okay.
call it.
I had a question again about the chiral centers because I went to go read it in the notes on page 9 of chapter 6, and it says that enantiomers, or like it deals with like when only the chiral centers swap, and I'm pretty sure for like the 3 and 4 relationship between them, I think all the chiral centers did swap. I mean, the only one that stayed the same was the wedge on carbon 5, but
Mhm.
that's not a chiral center because it has 2 methyl groups in it.
Oh.
Oh.
Right, that's weird. Okay, yeah, because it does say specifically chiral centers. Okay,
Must be opposite to the other compound.
that's evil. Okay. Chiral centers. Well, then I guess I wouldn't know what it would be otherwise then. So let's see. Okay. So let me just note this for myself. So I think it's actually this one. Because they also drew it kind of weird, so it's kind of hard to look at. Because basically, this one is like if you were to flip this like all the way around that way. So now these ones are dashed because they're going out. So it's basically these that are different. Let's see. Because only one part of this molecule is different. Or is it those are frick? Yeah, this one's kind of hard. Let me see.
So like I think the bromine swapped from wedge to dash, the OH swapped, and then the like methyl on carbon 4, that swaps. But then the one on carbon 5 is in a chiral center and that stayed the same. But otherwise all the chiral centers swapped.
Frick. I'm just like confusing myself kind of right now. Well, because what like actually happened with this image, I think so basically it flipped over like once, so it's flipped down, and then I'm honestly very confused. Or I guess you could just rotate it this way and I guess it would be the same.
This is a
Yeah,
lot.
okay, because you could wrote it this way on its face and it would be fine. So these are okay. Sorry, I'm so struggling to try and
Yeah, no problem. It's difficult. I might ask her about it tomorrow.
yeah. So okay, yes. So it's not flipped any like opposite way. It's just like rotated all the way over. So yes, so these are different. These are different. Okay, and then this one is now on the top and they're the same, but whatever. So these are different. Okay. Yeah, so these are the same. Yes, sorry, just had to figure that out for myself. So these are the same, but they aren't chiral, which is very true. Another question, yeah, because I'm not sure. Yeah, because then at that point I'm like, what would they be? Because they are different. Or well, no, because it wouldn't be constitutional isomers, because that means they actually moved. Yeah. Yeah, I'm not sure what they would be at that point because they aren't chiral. True. Another question for her, and I'm gonna write it down over here really quick. another thing to come back to. Cool. Okay. So for this one, predict which mechanism will occur. So SN1 or SN2. So we can look at, here, I just did notes on this one.
So it would be determine a good leaving group. I think that would be the first step. And bromine's a good leaving group.
Oh, okay, yeah. So the frick, hold on. The first step. Is it about the actual leaving group? Because
No,
or
that was
it's
just,
about this, right? This is
I
3 degrees, right?
was just following page 713, where you determine if it's a good leaving group. If not, then it's no reaction, and then you go by what it is. Is it methyl, secondary, and all of that?
true. Yes, the very first step. A very
And
good
then
one.
you go by what's on top of the arrow.
True. Okay. And then the good leaving groups, where did they go? That's
The only
just-
one that's not good is fluorine. That's it.
Yeah. So then the one that was OH, that one's not a regular one, right?
No, so that one is the what page was that one on? That one was on page 710. That one's the nucleophile, right? So if it's good, moderate, or poor.
Or well,
And
so I'm wondering, so yeah, so we know these ones are good leaving groups, but for B, this one's an OH group. Can that one leave?
oh,
No,
I
right?
actually don't know.
I don't think so. Here,
No, I
let
don't
me-
think that's part of a leaving group.
Yeah. Can anyone confirm? But I'm pretty sure, yeah, because it's just like BrCl and whatever the other one is.
Iodine, I think.
Yes. Yeah.
Mhm.
I'm pretty sure that's correct. Yeah, because we haven't done it with anything else like that. So yeah, so not that one. So yes, so that's the very first step. And then to check, let's see.
The nucleophiles.
Happen. Yeah, you could do that, or technically, well, just like the one that she did first when she was going over it, she said to check the carbons that they're bonded to. To check if they're, yeah, so this one's
A secondary.
degree, right? Oh, whoops.
I have a question.
Mhm.
Where can I find in the notes, OH is not a good living group?
Yeah, let's go ahead and
Thank you.
see. 'Cause- let's see. Hold on, let me see. Uh-oh.
I think 712,
What does that mean?
right above it.
Oh, okay. Sorry, but I did just see this, although OH is a poor leaving group.
Oh, okay, thank you so
Yeah.
much, thank you.
Okay, yeah. And then this one also kind of says it right here too. True. Okay. And then this one is, I'm gonna have this right. Also, wait. I'm having a huge stroke while trying to figure this out. This is a carbon, there's a hydrogen here. Is that also tertiary? Or is that no, tertiary, right?
So hold on.
No.
Secondary, I believe.
You think? Okay, then we'll all look. Oh, wait. Oh,
There
I
is
have
only 2
an
carbon.
example.
Only 2
Yes,
carbon
true.
secondary.
True. Okay, cool. Okay, perfect. And then did I do this one correctly then? This is gonna be 2 hydrogens. No, this is a lie. This one's primary, right?
Mhm.
Okay, cool. And then yeah, I'm looking at a picture that's making it easier now. I'll just put them over here just for help. X methyl. And then okay. Okay. Okay, that's all of them. They all look terrible right there, but that's okay. Anyway, so yes, so now we know this. So since this is a primary, the only one that does primary is SN2.
Mhm.
So it's SN2. And that's just like the rule for it. So it's just going over that earlier too. Two could be, or secondary could be either. I'll just write over here. SN2 only. Okay, so then we'll go to the nucleophile after that. And let's see. This is an ionic bond already, so let's see.
Mhm.
So whatever. So the rule is that SN2 needs to have a strong nucleophile and SN1 can have a weak one, basically. Yeah, sounds good. So, so I mean, I guess I'll just go SN2 from there, right?
Mhm.
Yeah, cool. And then, I mean, the other way to determine is the solvent type, and then this is also the solvent. So technically, just because I want to double check if it works both ways. So for solvent, protic means hydrogen attached to an O, and that's only for SN1. And then aprotic is H is basically not attached to O or N actually. That's SN2. Yeah, so it works either way because this is like, yeah, it'll be attached to the carbon anyway. Yeah, so they're both SN2. And then for that kind of thing, I would definitely just recommend like writing out all the rules for it. Yeah.
So aprotic is SN2, right? And then protic is SN1.
Yes, but for SN2, let's see. For SN1, this one can only work with a protic solvent, but SN2 can
yeah.
work with either, but it prefers aprotic.
Okay.
Yeah. Yes. I'll just leave it there. Cool. So that's that one. We could go to 6. Okay, I guess it's a word problem. A chemist has 2 vials labeled compound A and compound B. Each vial contains a pure substance. It is known that these 2 substances are either the same compound, enantiomers or diastereomers. State what physical properties the chemist should analyze to determine the relationship between the 2 compounds. My parents have the TV on so loud, so I'll actually be back.
Did anybody find this in the notes? Because I don't know where it explains like the physical properties for it.
Same, I couldn't find.
So I honestly just guessed it and said because the melting points are different, it means I don't know if they're diastereomers. That's just what I put. Like they have different physical properties because of it.
Are you guys nervous for this exam?
Yeah.
Same.
Mhm. Has anybody finished the second one? Like the second study guide or practice exam?
Definitely not for me. So then I did.
I think you're talking about the like compound A and compound B, right?
Yeah.
So at the end of chapter 6, I believe it talks about the different physical, like, it was the pre-recorded. She didn't go over it in class during lecture.
Mhm.
It's where it's like the polarized light and all of
Where
that.
did you say it was?
At the end of chapter 6. So it'll
Yeah.
say like enantiomers have the
Uh-huh.
same physical properties except for like their rotation about polarized light, and then diastereomers will have different physical
properties like boiling points and melting points and stuff will all be different. I think that's what that question
Oh,
is
I
referring
can't
to.
remember that.
You said it was towards
Yeah.
the end of chapter 6.
Okay, wait.
Yeah, it's the section that she had recorded for us.
Sorry, I thought it was streaming here. Yes. So here's some of it. Let me see. So rotation of pure. So diastereomers do not have the same rotation.
So like starting from the top of 611, it'll say enantiomers differ in optical activity, and then diastereomers have different physical and chemical properties. But if you look at the chart, it has enantiomers and diastereomers, and you'll see like the similarities and differences.
Thank you.
True. Okay. 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 So state what physical properties they should analyze. They could analyze like all of the properties basically. So like the molecular weight probably, right? Just anything on that table that was there, but I didn't really read it. Definitely like density. I guess we could just check. Oh, it wasn't even the weight, solubility, melting point, and then specific rotation. Solubility, melting point, yeah. Cool. Yeah, so any of those things are different. So is diastereomer with a E or an I right here? No, an I? This
In E.
oh, frick. Okay. Okay. Yeah. Anyway, so that's that one. And then we could go to 7. Predict the major products. That's terrible. Okay, let's see. Oh, the last one. Okay. Okay. This one is just hydration, right? It kind
I
of
think-
confuses me.
I think that's only for alkene reactions. I think
Oh.
it's actually an SN2 reaction.
Oh, frick. Oh, yeah, true. Okay. Okay. That's not really. Well, this one would be an alkyne one, I guess. This one is icky. Yeah.
That one actually, though, I wanted to ask her because H2O is a weak nucleophile, but it's a primary carbon, so it would have to do SN2.
Yeah, or well. Okay. Yeah, and then I guess would we be able to? Oh yeah, we would be able to predict the products. I guess. Not that I want to. Okay. Could we hypothetically do it? Yeah, I think. Is it worth trying, or would you rather ask?
I have a question.
Hmm?
If it's SN2, then we don't have any carbocation arrangement, right?
The carbo. Wait. If it's SN2.
Because
Yeah,
SN2,
that's correct. If it's
Yeah.
SN2, there's no carbocation arrangement.
and
Yeah.
you mean it's SN2?
For it
That
to
was
be
my only
H2O.
guess because
Yeah.
the only other reaction with H2O is hydration, but those are only for alkenes. Like you have to change an
Yes.
alkene to an alkane. So
Yeah, you're right. Yes.
If it's not SN2, yeah, it has to be a strong nucleophile. Yeah, she didn't really say anything about H2O specifically. I guess
Thank you.
technically it's not a strong one because it doesn't have a charge. I don't know. Yeah, okay. We could kind of leave that one. For this one, H2 and excess. That's one of the alkyne reactions. Let me see. I don't know if anyone knows off the top of their head how that one goes. Well, okay, so this is hydrogenation.
Yeah.
Yeah, but that one only does, this one's for alkenes.
So why don't we be focusing on the double bond and not the triple bond?
Oh
Or
shit.
no?
it should
Do
work
that.
for alkanes also. It would just go all the way to an alkane. Because if it's
Oh.
H2 and then like one of those metals will take you all the way to just an alkane. And then if you have like the H2 and Lindler's catalyst, then that's the cis alkene product. And then if you have the
Oh, okay.
NaNH3, that's the trans alkene product.
Yeah, this one, well, okay, I guess since it's an excess, then yes. Because it also confuses me because that one's like specifically supposed to be 2H2, and sometimes like it doesn't even say that. But yeah, I think that, yeah, that makes sense. Okay, so then, yeah, and then I wasn't even looking at that. So yes, so this one, it just adds hydrogens, right, to each side. Yeah, it'll basically just take it off. So this one. So it would basically just be like the same compound, just without any double or triple bonds, right? Or it would look the same, right? Put that one up, I guess. Right, because yeah, so for this one, definitely like it just basically takes this out and it adds hydrogens here, which don't need to be shown. So that part of it is good. And then for the excess, which would turn this into an alkane, I'm pretty sure it just also looks exactly the same. Right, can anyone confirm? No. Okay,
The excess
double
is going to affect the alkyne, the triple bond.
Yeah, because that's another one of the processes. If you have, it says like in the notes it's 2H2. We could just go to it in the notes just to double check how it looks too. Where is it? Here. Okay, yes. Well, I can't even tell what happened there. But yeah, it's just adding. I guess I can check 1, 2, 3, 4. 1, 2. Yeah, 3, 4. So yeah, when you add an excess of this, then I'm pretty sure you'll be able to do this reaction, which will just turn it straight into an alkane.
What page is that one on?
12.
512.
512.
Thank
Yeah.
you.
I think, yeah. Because you can't even tell where the hydrogens are because they aren't drawn in. So I'm pretty sure this will look like the same, except I turned this last one up. This is what I think I looked at, and then I was like, I need that. I have no idea what this is, just to get it out of the way.
I think the
So I
K means
can-
potassium, but I don't know what that has to do with
Well, yeah,
anything.
but-
So I
No reaction, yeah. I'm just gonna go with that.
What's the reason it's no reaction?
Okay. We basically we just said we would rule it out right now because we've like never seen that before. Yeah, it's not anything that we would, oh, is that an ionic bond? So strong, yeah, so it could be a strong
Yeah,
nuclear
so
bond.
there is a plus and minus charge, I
That's
think.
true.
But I don't know.
I
I
guess,
just
yeah, like,
I
'cause-
take things literal in my education. So like you said, if she hasn't shown it,
yeah. Because
But
I
I
don't
think-
remember her adding a K or potassium in anything. So I haven't tried that one at all.
yeah, I would just ask her. I would just ask her about it tomorrow. But the one above it, I
think that would be
believe
right. Okay, yeah.
that one
Um,
is gonna be an SN1 reaction.
I trust you, yeah, because I'm seeing that it's
Yeah.
product, I guess, first of all.
Because iodide would be the leaving group. Like it's chiral right there where the methyl and the
Mhm.
iodide are. So,
Yeah.
and the alkyl
True.
halide is
Okay.
a tertiary, so it would have to do SN1.
It's a weak
Yeah.
nucleophile, right?
And it's a weak nucleophile. Yeah, it has like a
Yeah,
partial
true.
negative charge.
Okay, so then for the product, let's see. Leaving group, please, and then it's basically deprotonation. Okay, so then for this one, I guess I'll just redraw it and then transfer it over. Okay. Damn, I definitely need more practice with these ones because, yeah, this would take me forever and ever. This is a leaving group. And then I guess, oh, okay, yeah, it'll be this one. This is going to be the nucleophile. And then since that one leaves, I guess this will be positive. And then there's also that methyl still here. So yeah, so this would attack right there. It would attach. Let me just duplicate it. No, I don't want to red actually. Okay. Okay. Yeah. I think. Okay. Okay. So it'd be like that, and then this one has a positive charge now. I'm pretty sure, right, or something like that.
Yes, so you would have to deprotonate and then
So we deprotonate with like more of this. So H3CO. When you do the deprotonation, would you? Oh wait, no, yeah, you keep the hydrogen in. Yeah. Yeah, and then it grabs this one, and then this one breaks off basically. So yes. Okay, cool.
If it has a metal shift or not?
Oh,
Sorry.
yeah, I think it does.
Yeah,
Yeah, definitely would.
I did a hydride shift.
Oh,
Yeah.
hydrated.
Yes,
And
very
then-
true that. This one, okay, yeah. So yes, just that would be attached. Okay, over here instead. Do I even have to show this like dash? No, that's a methyl, so yes. Okay, never mind. Okay.
Yeah, I think
Yeah.
you would. Because you have to remember like the enantiomer also if it's chiral.
Yeah, okay. Anyway.
But we would just go off of if we're determining like if it's chiral or not, we're not doing it off of the original carbon, right? We're gonna do it off of the one we shifted to.
Wait. Can you say that again?
Like if we're figuring out if there's a chiral center and then if it produces an enantiomer, we're looking at the new carbon that we shifted to, right? To see
Yeah,
if that one's chiral.
Does it have to be chiral to do SN1 or 2?
Yeah. The enantiomers
God, I don't
are
know.
chiral.
Oh, frick. Also true. Wait. Oh, okay. So, because now if you do move it over here, it's not chiral,
Mm-hmm.
right?
Mm-hmm.
Oh, okay. So maybe you just keep it the way it was. Yeah, I think that's true. Then yeah, because I'm like, I didn't even know that for SN1 it has to be on a chiral.
Oh yeah.
molecule.
And
Alright.
also I'm looking at my problem and I also didn't do that shift. I apologize, I lied.
Oh, okay, yeah, nice.
Natalie's also
No
right, 'cause it
worries.
was already a 3. That methyl is already a carbon attached to it, so it's already a 3'.
Oh,
So it is
okay.
chiral. That's why, because I
I'm
was
not
like,
gonna be
I have
able
an
to fix all of it.
enantiomer. Why do I have an enantiomer? It's because yeah.
Okay. Okay. Yeah, it is already 3. True. Okay. True.
Sorry.
Cool.
So it's
No, that's
right
fine.
like that without that hydrogen, and then it would have an enantiomer
Yeah.
because it's chiral.
I honestly, yeah, chiral. Didn't know that was a part of this chapter, I guess. Okay, but yeah, so it'll have the enantiomer too. Okay. So also same thing. Okay.
Wait,
Okay.
didn't she say that you're able to draw one of the structure and say plus enantiomer, or do you have to draw the second structure?
Oh, is that what she said?
She did, yeah. You could just put plus
Cool.
enantiomer.
Okay. Perfect. Okay. Cool. So yes, there's that one. I'm pretty sure that you could do it with D also. But yeah, we don't have to do it right now because she did not give us an example of that exactly. Okay. Yeah, we could just skip to D then. So this one, NaNH3 is one of the reactions. Okay, so that one's alkyne to a trans alkene. So I'm not sure how I want to do this. Let me see. What if I end up being a double bond? Like, I don't ever understand like the directions that you're going, like when to turn it like facing down or whatever. I'm pretty sure it'd be like this. Okay. And then like another one or whatever. That's so like incorrect. But basically, oh my god, it's so ugly. But yeah, right. How would you draw this actually? Anyone actually know how?
I
Like that's
just-
fine, or you can draw the double bond like slanted, like the one it's next to.
yeah.
The way it was kind of.
No, like how you have like how you do your normal carbon chains, just like curve, just
Mhm.
diagonal the
True.
double bond.
Yeah. Oh my god. I'm not even gonna try right now because I'll have a stroke. Diagonals. Yeah. So if this were like basically kind of rotated like and if that were a straight little thing. Whatever. Yeah, something like that.
I think that still
Yeah.
works though.
Yeah, whatever. She hasn't even taught us that specifically. This is, I don't know. Yeah, okay. So then 8. Fill in the missing. Yeah, I have no idea what this is. I don't think. The I have no idea. Does anyone?
That's yeah, it's just SN2 in reverse, like Natalie said.
Oh,
So you're just gonna replace it with like a BR with a bromine or iodide.
I literally have no idea what's happening. Okay. What? Okay, hold on.
So it's SN2 because it has a formal charge on the nucleophile.
Yes.
And so you're just replacing where in the product where it has the SCH3, that's where your leaving group was originally. So you're just, so you could just add any leaving group.
Oh,
basically.
okay.
I don't think she's,
Okay.
yeah.
Okay. Damn, so caught up in all like the tiny details. Okay, and then should it be wedged, I guess? Yeah. Or anything. Okay. 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 Cool. So then, yeah, we could do 8 then. Complete mechanism reaction. Okay. Okay, so first, okay, technically this happens first, right? It grabs this hydrogen. This one's by itself. Okay. So. Frick. Okay. 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 Oh, well. Is that what happens first, or is it, yeah, it has to grab the hydrogen, right?
Yeah, the bond goes for the hydrogen, and then the bond between hydrogen and bromine becomes a lone pair on bromine. Yeah.
So I guess I'm kind of confused because I know that one of these is going to be, well, I guess we automatically know that we want this one to be the carbocation so that we could switch it. So, okay, well, maybe it's fine.
Yeah, to do
And then
a
this one,
hydrolysis.
yeah, moves over. Um, okay. That one has a hydrogen. Yes, and then it adds to the side with more hydrogen. Well, that already happened, I guess. Yeah, so I guess we just didn't say, but it already happened that this one added to the side with more hydrogens, just like right off the bat. And you don't have to like show it anymore, I guess. Okay. Right. Is that like correct for the mechanism? Yeah. Did I do the mechanism right? I think so. Right?
Yeah.
That was so scary. I hate doing that. That's fine. Okay. So yeah. So then 10, provide another mechanism for this one. So hydration. Oh, frick. I hate this one actually. Let's see. Because I know this one does it like doesn't it turn into H3O plus and all that?
No, that should be an SN1 reaction, I believe.
Oh, really? Okay.
Yeah, because the
Mhm.
those are like alkene reactions. So anytime you see an alkane, it's going to be those
That's
SN1,
so
SN2
true.
basically.
That's so true. Oh God, we have so many reactions now. Okay. I wasn't even interpreting them before. Okay. Thank you. Okay. So I was literally just going over this last chapter, but I guess I need to do it again. So SN2 because this is well, okay, yeah, this is tertiary. So yeah, SN2 and okay. Okay, yeah. So leaving group.
It's SN1 actually. When it's
Is it? Oh.
SN1 is only 3 or tertiary carbons.
Oh, okay. I read it the wrong way. Okay. Sure. Okay. 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 So show the whole mechanism. So okay. This one would grab the leaving group. Wait, no. Wait. Does it? Let me see. No, yeah, because it just leaves on its own.
I'm so sorry, what's your question?
It's okay. I'm gonna have a whole entire stroke right now. Yeah, if anyone can just help me do the reaction if you want to do it.
Okay, so the leaving group leaves.
Yeah, so I guess I'm just
And
like, how do I
then-
have to show that? Or it just kind of does?
It just you can show the carbocation in intermediate. So,
Oh, what just happened? Okay. Sorry.
so where you have your two methyls right there, that'll be your carbocation. And then you can
Okay,
just show the lone pairs
BR, yeah,
on
true. Okay.
the water, on the oxygen on the water attacking
Mhm.
that carbon.
Okay. Sure.
But she
Okay.
might be specific about where your arrows are pointing. I feel like she marked me off a
I
couple.
hate that.
with
Okay.
last exam, and I'm like,
So what,
"That's
just like
good."
exactly to that
Like, how do you?
little
Yeah,
carbon
like
part?
she's
That's
yeah.
so stupid. Okay. That's nearly it. Okay. So then.
So it's like doing its nucleophilic attack, and then it has a positive charge, so we have to deprotonate.
Okay. And then deprotonation, yeah, with another H2O. Okay. Oh. Cool. Okay. Okay. Yeah. Anyway, that was the end of it anyway. True. Okay. Okay. I think if I have this steps, I'll be okay. Okay. Cool. Sure. The last one on this one. Okay. This is terrible also. Okay. Provide the reagents necessary. Please stop. You guys can see that call coming in too, right?
Yeah.
Okay, here. Give me 1 second then. Hold on. Please stop. Okay.
Are you here? Hello?
She's still there. She was just trying to fix something.
Anyways, okay. Thank you. Okay. provide the reagents necessary. So I assume the first one, it'll have to be like, let's see, the one that adds hydrogens to both sides of the alkene, hydrogenation. Right?
Well, you have to create a leaving group in order for
Mm.
OCH3 to attach,
Mm.
I believe.
Oh, okay. True. Oh, okay. So I guess it could be, so just hydrohalogenation then?
Yeah, like
Okay.
HBr, HCl, I
Okay.
think. Or HI.
So HBr first. So that would just have us do this, and then the hydrogen would be added over here, and then wait, no, hydrogen added over here, and then we'll have the Br right here. So that'll be our first thing, and then, or yeah, it's the same thing as that. And then the second one is basically going to be this. I'm just, let's see. So this is connected to a tertiary one. So it's going to be SN1, meaning it's going to do deprotonation, right? So I'm thinking it'll be, well, does it have to? So I guess I'm wondering,
I think
If
it
we need another
I
hydrogen.
have to ask her that, but I put a hydrogen there just because.
yeah, it's SN1, yeah.
But yeah.
Okay.
But,
Yes.
and then I just
Okay.
put 3 deprotonation. I just wrote out deprotonation because I don't know how she wants us
Oh,
to write out that as a step either. It would just be like 3
yeah.
HOCH3 again. So like it's kind of weird.
Okay. Yeah. Yeah, I feel like we probably won't have to do it, but yeah. Feel like it just comes with the territory. Okay, cool. So yes, so first we created a leaving group. So we did that with the HBr, and then it added over there. And then this is a tertiary carbon. So yeah, so we decided it's SN1 because it's 3-degree carbon. Yeah, basically what I already have. Yeah. Does that one make sense for everyone? That one was the easier one.
Yeah, it does.
Cool. Okay. Definitely just need more practice doing those reactions up. Cool. So that's that one. We could go to the other one now. Everyone's cool.
I gotta go, but I couldn't get to the beginning of this one. But
Oh, yeah, no
tomorrow when we redo it, I'll be here for the whole meeting and stuff, or whatever we do tomorrow. I'll be there for the whole
Yeah.
meeting and stuff.
Sounds good. Yeah, there were a few that we weren't sure about. I know I was literally gonna spring it on you as you were talking. I was gonna be like, oh, we don't know about these ones. But yeah. Okay, yeah, we
Sorry.
could go
Yeah,
over
so we can. Yeah, there's
to
some
the next
I'm
one.
not confident either, but we can like work through them.
Yeah,
So
Cool.
um,
Okay.
I'll
Sounds
see you guys tomorrow.
Okay, see you. Bye.
Bye.
Thank you so much.
Okay, but we could go ahead and keep doing the second one. Everyone wants to keep going. Hopefully it'll be faster this time. Let's see. So we can just start with the first one. The one I know how to do. Okay, well, mostly. Let's see. So I'm gonna start numbering it, and I'm gonna number it this way because it has the alkene, or well, the double bond closest. So 3, 4, 5. And then you want the longest root, so 7, 8, 9. So that's gonna be nonene, and then also the 2 to specify where the double bond is. Okay. So there's that, and then right here we have 4 dibromine or dibromo. This one is, I don't know, let's see. I'm not sure what this one's called.
Is it purple?
Yes, that one. Okay, cool. Cool. Yeah, I just always forget this. Okay, yeah. So those are all of the groups coming off, and then you put it in alphabetical order when it comes to the substituents. So 4,4 dibromo, 6 6 propyl, 2 nonane. I'm pretty sure that's all of it. Yeah, so that one was easier. Cool.
Wouldn't it be E because the
Oh.
alphabet?
Yes, yeah, you could definitely do easy. Oh my god, I always make, or well, I guess on the last one I also didn't specify that. So yes, these are, it's trans because you can see this is hydrogen, this is a hydrogen. They're on different sides. So yeah, it's either
E or trans?
trans or E. Yeah.
If you use E terminology, do you have to put in parentheses?
I'm not sure. Okay, wait, let me
Or
see. Let's see. I think that's. I think she might have had it. I think chapter 7 in the beginning. Was she doing nomenclature, or was that a different one? Let's see.
I'm looking
Mm.
at
Oh,
chapter
it is.
6. I don't know.
Trans is not in parentheses, but I
Yeah,
don't know
I just
about
went with
EC.
trans and put the dash, but I just wanted to know for the E.
Yeah.
That's okay, we got one.
Yeah, I'm not too sure. That's cool. Okay, yeah. Trans also works. Yeah. So yes, there's that one. So then for 2, determine, oh, this is great. I love this. All right. Is it gonna do a rearrangement? Yes or no? Yes. Okay. So yeah, boop, right there. And then we'll end up with something like this-ish. And then it's right here. I didn't even read it all the way. So indicate the type of shift. So this is a hydride shift. And yeah, draw the expected rearrangement. So yeah, it's that one. I'm sure that was good for everyone. Okay. Oh, okay. This one, determine if it's R or S, basically. So I'm gonna grab the periodic table just to compare BR and F. So it goes by the higher atomic number. So BR has a higher one than F. So this one's 2, and then 3, and then 4. So 4 is dashed, so that means it's like in the back. So you're basically just gonna like ignore this one. So you're going in this direction. So that is clockwise. So it's R, right? I'm pretty sure that's cool with everyone. Let's see. So then this one.
Wait, for that one,
Yes, please.
I did it different. I did alcohol was the number 1 and then bromine was number 2.
Oh,
So I'm not too sure though.
yeah. So it goes by priority. It goes by atomic number. So the atomic number for bromine is 35, and then fluorine is 9, and then oxygen is 8.
Okay.
Yeah, it says that in, I don't know which of, I guess that's chapter 7. No, 6. Yeah. Okay. Then for this one, so this one's gonna be primary, and then this carbon will be secondary because it'll have the 2 carbons attached basically. And then this one will be tertiary, and then or whatever. I don't even think it's supposed to be like tertiary or whatever, but yeah. So when it's wedged, then you basically do the opposite direction that you record. So you go 1, 2, 3, and then oh shit, yeah, whatever. And then it goes back around this way. So this is clockwise also. Yes, so this one's also R. Sorry, I'm going kind of fast, but yes. Quite sure that's right. Is that cool for everyone?
Yeah, I got R for that one.
Okay, so perfect. Now we know this one. Chemist has 2 compounds A and B. Each vowel is pure. Are they the same? Enantiomers. Yes. What's the relationship between these? And explain your reasoning. So they have different boiling points. So that would mean that they're diastereomers. Let's see. Where did that go?
If it's an enantiomer, what relation between boiling points or other?
Yeah, so we were talking about this for the last one. It was here, I'll just go back to it. It was at the end of chapter 6, and it says that enantiomers will have like all of the same properties, and then diastereomers are going to have different properties. And then of course also the other option was like the same compound, and they also have the same properties.
Thank you.
I guess that's all I would say. It's briefly explained, but that's kind of all it gave us, that they'll have different properties if they're diastereomers. So yes. So that's that one. 5, determine the relationships. So this one, I'm pretty sure this is the same. Let's see. I guess we could just 1, 2, 3. Yeah, 1, 2, 3. Yep. So those are the same compound. That was nice. This one, it's gonna be the same thing as this one. Okay, so for this one, well,
For that one, I put unrelated because the first one has 4. Because I don't think you start your one at H.
yeah, you don't want. Oh,
So-
but so here, I think here. Wait, so let's number it 1, 2, 3, 4. But then this is 5. 'cause
Oh,
this is
5.
another
Never
carbon.
mind. Yeah, I just saw that.
There's 1, 2, 3, 4, 5. Or well, I technically, yeah, numbered it the wrong way. Let's see. 1, 2, 3, 4, 5. Yes. So this one, if it so for me, it would be easier if I could like flip this one. So let me see. Try and draw it backwards, I guess. Hold on, let me see. Okay, so if I flip this, then this is gonna be a dashed OH, and then oh whoops, here wait. That's weird. Wedged CH3. Okay, right. And 1, 2, 3, 4, 5. Nope, I give myself an extra one. Let me up. This is so ugly. Okay. So 1, 2, 3, 4, 5. Okay. Sorry. So I just had to flip it for my own sake because it was getting kind of confusing when you look at it. Because let's see. So PhD, they're kind of all like changing positions. So let me see. I'm not sure about this one. It kind of looks to me like it's just like rotating and they kind of look like the same compound. I thought it would make more sense if they did it like this. Let me see. Because now this one's like, I thought it would make more sense, but now this one's just a line and this one's dashed and this one's dashed or wedge, whatever. I don't know if anyone has any ideas for that one.
I don't. I absolutely hate these.
Yeah. I guess, well, for this one, I would just make a molecular model if it's too hard. So let's see. I'll just share my screen in a second.
For this one, I thought it was really hard too, but for number 3, I just drew it mirrored. And then so it kind of looked like number 4, except I think there were like 2 things swapped. And then if it's mirrored, then that means it's already the enantiomer.
Mhm.
And it's so like
I
back-
know. That's what I was kind of trying to do. I tried to mirror it and then it was still weird because that only changed it changed this one to a wedge, but the other one to a line. I don't know. Here, let's see. But I have a molecular model, so let's see, put this on. Give me a second. Okay. Okay. So can I see myself? I am now showing my face again. So this is kind of it. So it has 5. This is going to be the oxygen, and then this is a hydrogen going forward. So for it to be okay, so then sorry, I'm starting at the number 4 one basically. So it's this way. I would just turn it around this way, and then saying that the OH would be forward, but then this would be back, but they're also both facing up. So I don't think that it works. So what's the name of it when basically like these 2 would have to be changed?
Wait, actually, I kind of remembered something from the homework. I think and the way you can tell is by the R and S configuration of the
That's so true. Okay, wait, I haven't tried that yet, so let's do that. Okay, so R and S for this one then. So yeah, let's do that. So 4, 1, 2, whoa, 2, 3. Yes, and then this one. 1, 2, 3, 4. Okay, so this one is the easier one. So it'll be this way, except the opposite way. So this is counterclockwise. So this one's S, right? Sorry, I went really fast right there. I'm pretty sure. Yeah, and then for this one, you draw the whatever what is this called? I don't know. I don't remember. Circle thing. So then the OH, sorry, I'm gonna look at it. Let's see. I'll look at it from this way. Yep. So the OH is on this side, and then the CH3 is on this side, and then CH blah 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 is on this side. So that's 1. Wait, no, sorry. That's 1, 2, 3. Going this way. That's R. So they're diastereomers then, right? Or does that mean they're? Wait, but what does that mean? Does that mean they're enantiomers or diastereomers?
I'll go check the notes really quick.
Yeah, we can. It's kind of like, so I'll whip in chapter 6 too. Hmm. Oh, do we have 2 chiral centers? Don't think we do. Oh. So I'm thinking right now they're enantiomers because they don't have 2 chiral centers. They only have 1.
That's what I thought.
Okay, cool. So we'll just go with enantiomers here. Perfect. Cool. That was great. Okay, awesome. So yes. Okay, so then we could go on to 6. So determine if it's going to be SN1, SN2, or no reaction. I'm going to go ahead. So first we could look at the leaving groups. So we have Cl, that works. This one is fluorine, which does not work. So I'm going to go with no reaction already. This one also works. That's the first step. And then let's see. So next we would check the carbon it's attached to see what kind of carbocation it would be basically, or whatever. So this one's tertiary. This one is, what? Is this primary? Yeah, I think. Well, no, I think this is secondary, right? And oh yes, and this is primary, yeah. So then based off of that, so SN2 does primary. So go with SN2. And then this one is tertiary. So SN1 works with tertiary ones. Oh, and then, yeah, that was this one, which was no reaction. So that's kind of easy. So there's that one. Okay. And then we could go to 7 then, unless anyone has any questions. So, oh god, this is gonna be terrible. Provide the missing reagent. I hate doing this. So first, I'm pretty sure we would have to take the chlorine out with like SN1 or SN2. And then this is a, yeah, secondary, so it'd be either, I guess. Yeah, and then we could choose a nucleophile, so that's fine.
Isn't there something about like things being like added from like the same side or like from a certain direction, whether it's SN1 or SN2?
Oh, with SN1 or SN2, I'm not sure about that one. Yeah, like syn addition, like, yeah, that's what it sounds like to me. Yeah, syn addition or like anti-addition, but I only know about that for alkenes.
On page 5 of chapter 7 notes, like it says something about like for SN2 reactions, there's like a backside attack, but then for SN1 is when you would get both types of enantiomers because
Yeah.
So I think it is SN1.
That is an amazing observation. Okay, SN1 is the only one that does both, right? Is what you think? Yeah, because it can attack from either side. Beautiful. Okay. Oh, well, yeah. So this way would be SN1, but still asking to provide the missing reagents. So I guess the first one could like literally be anything. What are common ones for SN1. Let's see. SN1 needs a strong nucleophile, so I guess I'll just go and find one. Okay. Yeah, so we could do like HBr, I guess. Yes. That looks wrong, but is correct, I think, for the reagent.
Oh,
Yeah.
wait. Wouldn't it be water because we added an OH group?
Well that cause so let me see.
Like, isn't it the
'Cause I'm-
nucleophile that determines like what gets attached onto the, like where the CL used to be?
In SN1, I freaking obviously like need to go over each of these reactions, but I'm thinking for SN1, does it, let me see. Oh frick. Yeah, the product does stay attached. Oh my god, I'm gonna have the worst stroke. Yeah. So yes, H2O. And then okay, and then that'll be like the only reagent, right? Because I thought we were gonna end up doing like 2 of them. Yeah, and then the other one would have to be, nope, I'm so wrong. Yeah. H2O, and then it's a SN1 reaction. True. Okay. So yeah, and then that one I guess just makes 1, so SN2, but I hate this one, I'll die. Anyone have any ideas? So immediately. I'm sure that's SN2, right?
This is where I stopped on the exam, so I'm sorry.
Yeah, no, understandable. Yeah.
Like, I'm gonna do this tomorrow and then I'll be better prepared
Yeah, no
for
worries.
the next
Okay.
meeting.
Okay, so then I'll just skip the ones that are hard. Let's see. I don't even want to do these right now. I'm all over it. Let's see.
I don't
Ew.
blame you.
Okay. Are we all over it? I think yes.
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 Okay. So tired. Okay, cool. I'm definitely gonna do the chapter 7 homework right now then, because yeah, that'll help me practice. Cool.
Yeah, like, I just kind of did the first part of that, so the reason I remembered this. I can't believe you guys remember all this stuff from chapter 5. It's amazing.
Oh my god. What even?
You
I
know
don't
what
know
helps?
what-
You know what helps is like, I got my cheat sheet that I did. I do a cheat sheet for like every quiz. And then for this one, I did all of the reactions. And then I did like an example and then I wrote down the page number. I don't know if that might help, but it goes all the way to chapter 5. Chapter 6 is more like the R and S, and then
Yeah.
chapter 7 is like the SN1, SN2. So that's
Yeah.
what helps me.
Yeah, I was also saying that I am simply looking at, I have a bunch of like little flashcards with all of the reactions from chapter 5. So yeah.
Yeah.
And then definitely on the front for these ones, which was kind of helpful, I have like hydrogenation or whatever, or no, sorry, this is hydrohalogenation. And then I have like the reactant, so it's like HCl, HBr, HI. And then I have like each of the things that come off it. So it's like H plus and then 1 X minus, whatever it is. And then it's in Markovnikov fashion. So then I could just look at the front mostly. And then on the back, I have an example too.
That's good too.
Yeah. Yeah. Okay. Well, now we know what we're lacking. So we'll meet again tomorrow at 5:30. Yeah.
Okay, thank you, Desiree.
Thank you so much.
Yeah.
Thank
Bye.
you so much.
Of course. Okay. Bye.